we're going to get started. Okay, so now I'm going to explain to you how to do the first couple of questions on the back side of homework number 2. Okay, so when you see the instructions, order them in increasing atomic size, what does that mean? Anytime you see the words increasing anything, it means that you really have a situation where you have like big, bigger, biggest. So it means that the biggest thing is last in the list. This can really be confusing, so you have to pay attention to what you're doing in order to make your lists proper. Decreasing is exactly the opposite. Decreasing is like biggest, bigger, big, or small, smaller, smallest. So in a decreasing set, your biggest thing, oh, my G got a little funky. Your biggest thing is first. Because over the course of your list, you want the things to get smaller. So your item that's biggest has to be first. Now remember, when you're talking about electronegativity, noble gases, or groups 8A, they will always, no matter what, have the smallest electronegativity. That's not true for any of the other periodic table trends, only electronegativity, because they have none. None is a smaller number than any other number, no matter how small. So for electronegativity, you have to have the noble gases being the smallest. So if you're looking at page 1 of your homework, and you look at the very last question, if you did not choose helium, you did not choose correctly. Any questions about that? I'm so sorry, Ms. Burton. Cameron's here. I'll submit it real quick. I'm sorry. Thank you. That was my first field one I messed up. All right. So now you have all the skills you need to finish those first couple of questions on page 2. Yes, Carter? Electronegativity. All right, I am going to, has everybody done writing? Okay, I'll give you a minute. Oh, this is going to be annoying. Sorry, fellas. The fan is blowing my tablet. All right, so take out your periodic tables. We're going to need to put our thinking caps on because this is a little complicated. Once we get through it, it's pitifully easy, but it's one of those things that you're not good at it until you're good at it. So I'm sure that if you play a sport or a musical instrument or you do anything in life, there is some concept that you have had to like work really hard at and you were terrible at it until you were good at it. This is one of those things. I apologize. It's just the way it is. All right, so today we are going to be learning the concept called electron configuration. Oh, wait, no. 10. We end at 10, like on the hour. Okay, that's good to know. Okay, so a little bit of background, and I'm going to explain to you hopefully why we care about this. Why should we care about it? Unless you are planning to be a chemist when you grow up or take a lot of chemistry in college, you'll never use this again. And really, truly, that's kind of a thing in all of the subjects matter that I'm going to teach to you over the course of this whole year. You can get through life just fine without knowing anything about electron configurations. But why do I teach it to you? Well, there is a real beauty in training your mind how to think. And if you can train your mind how to think in this detailed, systematic, routine way, you can do a lot of other things. There's a reason that if you want to be a doctor or anything in the medical field that requires a lot of complex, like linear thought, like if A equals B, B equals C, that type of thing. If you want to do anything in the medical field or any kind of like engineering or anything, most colleges will require you to take a lot of chemistry. Not because you need the chemistry to know how to be an engineer. You certainly don't need the chemistry to know how to be a doctor. You need to take chemistry to train your mind to think in these ways. And so you're never going to need this ever again, unless you take more chemistry, and then you will need it. But the world is not based on people who know this thing. But if we can train our minds to think and to like control all of the details that you will see here, you are well on your way to being able to do higher level of thought. So I know that this is useless information for you, but I like it and I think it's fun, so you should do. Okay, this is the last time I'm going to write the word electron. I'm going to use the E minus because I'm lazy. Electrons all have the same charge. Do you remember what charge they have?
Negative.
Correct. What happens to like charges? Do they like each other? No, they don't. They repel. But all of the electrons have to fit in the electron cloud of an atom. But all of those charges are repelling against each other. So imagine that you don't get along with your siblings. Raise your hand if you feel that way, that you don't get along with your siblings. If you don't have siblings, then you're golden. You're the golden child. So imagine that you have a sibling that you really do not get along with, and you are forced to share a room. How do you feel about this thing? Not great. That's how electrons are. They have to be all separated into their own separate rooms in a very orderly way. Otherwise, they're going to be unhappy. Unhappy electrons cause damage, and they do bad things. And so we have to keep our electrons happy.
Okay.
So that means that all of the electrons in an atom must be properly ordered to eliminate fighting between them. My sister and I didn't get along when we were in high school. We're 2 years apart. I'm the oldest. We shared a room. We got to the point where we like had a piece of masking tape on the carpet that separated like my side from her side, and if you like any of your stuff or like your foot crossed over the line, you get your ass beat. It was great days. So to prevent that in the electrons, they must be properly ordered. Yes, sir.
What do you mean by property?
That's a good question. What do I mean by that? AKA, they must be put into their own proper places. And I'll explain what I mean by the proper places in just a second. I'll let you copy that down. How many of you are thinking about taking AP Chem next year? Okay, good. You should. You should. It's a good time. The proper places for the electrons have a special name. They're called orbitals. And they get that name because that's what they look like actually in real life. So your atom, I can't draw it because this is a two-dimensional object and atoms are three-dimensional, but, or actually, let me get a ball. So this is what your atom looks like. It's pretty spherical in nature. And the way that the electron cloud is like spatially made, or like what it looks like, is something that like do you know what the word orbit means? Yes. And so that's what the electrons do. Like they go around the sphere. Like, so if you were an astronaut in orbit, and like this was Earth, you'd be going around the Earth. Electrons are in orbit around the Earth, which is their nucleus. And so that's where the name orbital comes from. There are 4 different types of orbitals, and they all have a different letter. That's their name. The first orbital is S, then P, then D, and F. Where did those names come from? I don't want to tell you.
So,
It's just complicated. S comes because like the S orbital looks like a sphere. P looks like it's called the pi orbital. It doesn't look like a pie that like you eat. I don't know why it's called that. D looks like a dumbbell, like when you lift weights, a dumbbell. That's what it looks like, and so that's why it has the D. And I don't know why F has its name. So each one of these orbitals can hold a certain number of electrons. The S orbital can hold 2 electrons. The P orbital can hold 6 electrons. D can do 10. And F can do 14. Say that again? Yes, but yes, that's true, Carter, but it's like kind of more complicated than that. I'll pull up a picture of it for you later. Okay, so the S orbital can only have 2 electrons. It can't have any more than that. P can have 6, D 10, and F 14. You can think of these orbitals as like different rooms of a hotel. So there are some rooms that are small, right? They only have 2 beds. And then there are some rooms that can sleep a lot of people because they're really expensive and they maybe like cover the entire floor of the hotel. That would be like the F orbital. All right, so now I want you to draw in your notebook. I don't want you to write this on your periodic table. I want you to draw it in your notebook because later you can figure out a way to put this on your periodic table. Everyone is different though. All right, so draw yourself your little thing. Make it like medium size, like not the whole page of your paper, but like don't make it too small, otherwise you won't be able to recognize it. So I'm going to use this because my drawing is so bad. I'm going to draw on here, but I don't want you to draw on your real periodic table. I want you to put this in your notebook. All right, so the beauty of how the periodic table is set up helps us to know electron configurations merely by looking at where an element is in the periodic table. So that's what we're going to do today. We are going to figure out how to pick a random element and know what its electron configuration is. All right, so the S block can have 2 electrons in it. This region of the periodic table comprises the S orbital. That says S orbital. The p orbital can hold 6 electrons. So I'm not drawing a circle around those 2 bottom rows. I'm only drawing a circle around these main columns here. This is the p orbital section. Sometimes we call it the p block. The transition metals in the middle, that's the d orbital or the d block. The d orbital can hold 10 electrons. And then the f orbital is the rest of the periodic table that we haven't even talked about yet. That's those last 2 rows. Do you remember what those rows are called? Elliot? Lanthanides and actinides. Yep, you were very close. All right. So that's where the orbitals are. Now let me just show you about how brilliant this is. The s orbital can only hold 2 electrons. How many columns are in the s block? How many? So the p orbital can hold 6 electrons. How many columns? 6. How many electrons can the d orbital hold? 10. There's 10 columns, so there can be 10 electrons. There are 14. 14 electrons, so there are 14 columns. There are very few things, I think, in life that are this neat and orderly, and so it makes my heart a little bit happy. Okay, so now let's talk about the rows of the periodic table. So the rows have numbers. And those numbers have a special name. Those numbers are called quantum numbers. Quantum numbers describe how much energy an orbital has.
Wait, what did it say? Rows have?
Numbers. Rows have numbers. Those numbers are called quantum numbers. Quantum numbers describe how much energy electrons have. The higher the quantum number, the higher the energy. So we can order, now this I do want you to write on your actual periodic table. We can write in the numbers for, we'll use orange, each of the rows, each of the periods. There are 7 main periods, 7 main quantum numbers. Hydrogen's row is number 1, lithium is 2, sodium is 3, potassium is 4, rubidium is 5, cesium 6, and francium 7. Now, it would be nice if it was just as simple as this, but it's not. So each of the different orbitals has its own way of numbering the quantum numbers. S and P are the same though. So this is still row 1, 2, 3, 4, 5, 6, and 7. S and P are the same. D and F are both different and they're not the same as each other. D starts numbering, like, so the D block starts at scandium and its number is 3. So there are only 3, 4, 5, and 6. Those are the only quantum numbers that D has. And then the lanthanides come off of lanthanum. So if they were to have the same number, you would think that cerium would be also like quantum number 5, but it's not. It's 4. Why is it this way? Because that's the way God made it. No, just kidding. The D block has less energy than the S block. And so we have to indicate that. We can't just say, pretend that this electron has the same energy as this one, because it does not. And the fact that these electrons have less energy means that they're able to, all of these elements in the D block are able to do a lot more different bonding than the elements in the S and the P orbitals. But what you really need to know, you don't need to know why it's true, you just need to know that it is true or how it's true. Does that make sense? So if you write these things on your periodic table, when you come to a test, you should be able to know what to do. All right, so take a cleansing breath. Let it out. Take a cleansing breath. Let it out. Take a cleansing breath. Let it out. All right, let's talk about how we do this. So I'm going to leave that up on my screen and I'm going to go old-fashioned style. And I'm going to show you how we actually do this. Now, this is pretty easy once you get it. But until you get it, it's gonna, like, every word that comes out of my mouth is going to sound like gibberish to you. So accept the fact that it'll be gibberish until you get it, and do not be impatient with yourself. And don't be impatient with me. I'm doing my, no, just kidding. It'll be fine. You'll see how easy this is. There is only one exception to this, what I'm going to teach you, this rule, and it's the second element. So once we can get past that one exception, you'll be golden. Okay, so this is how you write an electron configuration. There are 3 components. The first thing, you need to write your quantum number. And so let's just do hydrogen. He's the first friend. So let's get started with him. Hydrogen is in the first row, so his quantum number would be 1. The second thing that you're going to do is you're going to indicate the orbital letter. Now, all of those orbital letters, my friends, are lowercase letters. Okay, so you wrote on your periodic table or on the one on in your notes, and we can see that this is the s orbital, right? So the orbital letter is
S.
all right. Now, the last thing that you're going to do is the hardest one for me to explain. So I'm going to write a way to do it on the board, and then I'll try to give you several different ways of explaining what I mean, because it's a little confusing. So now you're going to write the number, it's hard for me to explain. Write the number of columns, not the number of numbers, Michelle. Write the number of columns you move through to get to the element you're trying to write the electron configuration for. Write the number of columns you move through to get to the element. For example, I have my little blue dot here by tin, and so if I were to do this for tin, pretending that I have all the rest of it done, how many columns would I get through? Of that block only, 1, 2. So that's the number. I know. Carter?
Is it like by orbital? So
Yes, by orbital only. Not, like, so if we're here, I'm not going to start from here to count 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to start in that orbital that I'm looking at. So what column, so maybe a better way to describe this would be, what column of that orbital is tin in? So maybe I'll write that. What column is what column of the orbital, that'll help us to remember that, like, not of the row, but of just that section. What column of the orbital is the element in? So I think this is a better explanation than maybe this one. Okay, so now if we have to look at our example of hydrogen, what column of the S block is hydrogen in? 1. That's your number. But that number is a superscript. Do you know what that means? It's in the upper right corner. So superscripts go up here, subscripts go down here. But we want it to be like a high up number. So the electron configuration for hydrogen is 1s1. All right, so I told you the exception, the only exception is the second element. So trust me that this is true. It's 1s2. So if we were doing the rules that I just taught you to do, what should we do? Well, we've got 1s1 for the hydrogen, but then helium is over here and he's in the p block. So shouldn't he be 1p1? He should be, but he's the exception to the rule. And the reason for this is because if you can imagine the electron cloud as like an electron hotel, every orbital is a new floor of the hotel. If you open a new floor of your hotel, you have to hire a full cleaning staff for that floor. It's too expensive to do that. If you still have rooms left open on that first floor. In the same way, it's true for electrons. It costs too much energy to open up that p orbital when there's still room in the s. Because remember, how many electrons can go in an s orbital? Not 1, but 2. So we have to fill that orbital before we can go on to the next one. So that means that 1p is not a thing. There's no such thing as the 1p orbital. Because there aren't any electrons to put in it. So why open a floor of the hotel and staff it? It'll cost too much energy. So we don't do it. Helium is the one exception. Okay, so now the next element is lithium. And so part of filling up your electron hotel, once you have electrons that reside in the hotel, they will always be in their same rooms. So lithium has 3 electrons. Lithium's right here. Lithium has 3 electrons, so that means I need to have all of my little superscript numbers add up to 3 to indicate that I've got 3 electrons being placed in their rooms. So lithium already has the 1s2 orbital filled up because we have to account for the fact there are those 2 electrons up here. But now let's do what we're supposed to do, write the quantum number of the element. So lithium is in row 2, its quantum number is, and what orbital block is it in? And what column is it?
Or does it have to add? Does it have to add?
It has to add to 3, but you can know that because lithium is in this first column. So that means it's in column 1. That's the number that goes above the S. Okay. How bad do you feel?
Wait, is lithium not beryllium?
Lithium is this entire thing. All right, so doing what we did before. Why is it what?
Where did we get the 1s? What is that? Why go
I said
2s?
Because if you only have 2s1, you are only saying that you have 1 electron. And lithium has 3 electrons. How do I know that? It's element 3. And remember, if you don't have a charge, protons and electrons are equal.
So do the big numbers have to add up to 3?
No, the small numbers add up to 3. The big numbers don't matter. We don't have to add them up to. They do matter, but not for. The little numbers are what tell us how many electrons. All right, so beryllium has to add up to 4. So the 1s2 is full. If it's full, we just copy it down. But now, what about beryllium? So let's follow the instructions. It says to write the quantum number. That would be 2 still. Its orbital is S. What column is beryllium in? It is 2. So, do you see what I did not do? I did not do 1s2, 2s1, 2s1. You will see that when we start getting to these bigger elements, you could do that, but it'll take you so long and so much hassle that we don't want to. So we only are going to copy down orbitals that are full. Let me say that again. We are only going to copy down orbitals that are full. The rest you have to figure out using this method. All right, our next friend is boron. So, boron. All right, so are both of these S's full now?
Wait, I don't understand what you mean by
It's full if it has its maximum number. So remember how we said that, hang on, wait for it. The S orbital can hold up to 2 electrons. That means it's full. So when we get to P, how many will it have if it's full? Good, remember that. All right, so let's do boron. 1s2 and 2s2 are both full, so let's just copy them down. Now, what row is boron in? Well, I'm just going to look over here because now I'm over in this P block here, and I want to make sure that my numbering is the same, and it is. So that means I've got 2. And then what's my orbital? What block am I in, Elliot? You are in the P. That's correct. Now, what column is boron in of the P? That's correct. 2p1. All right, I think you're not going to be able to see it anymore if I keep writing there, so let's do this.
Yeah, something you just added.
Like going down this way?
Yeah. You can just keep the one as how can he go?
What?
How high can he go?
How high can he go? He can go to 6. All right, we're gonna keep doing these until this makes sense to you. Oh, damn. Okay, hang on. Carbon is after boron. So let's copy down the orbitals that are full. 1s2, 2s2. What row is carbon in its next block? 2. What orbital is it? And what number column is it? All right, so then check your math in your mind. Carbon should have 6 electrons, 2, 4, 6. We're good.
So what happens if, like, on the test you start like on random?
We'll get to there. I'll teach you that. After carbon comes, oops, not oxygen, nitrogen. All right, see if you can do this by yourself. And if you can't, don't worry about it. I'll give you the answer.
Yep.
All right, then finish out this row. O, F, and neon. For oxygen, I got 1s2, 2s2 to be 4. One S2, 2s2, 2p5. And then neon is 1s2, 2s2, 2p6. So now when you get to the end of a row, or to the end of any block, you know that it's full. All right, so now let's make things even more complicated. Let's try doing sodium. If these orbitals are full, and we just said that P was because it's got 6 electrons in it, we can copy all of these things down. Now is usually the point when you're thinking in your mind, do I have to copy these down every single time? Yes and no. I'll show you the no way in a little bit. Okay, so here I've just copied down the things that are full, but how do we end sodium? Follow those rules. What row is sodium in? What orbital is it? Is it? Thank you. And what column? Nothing. Is S full? Is S full now? No, it's not. So the next one is magnesium. Let's do magnesium then. We can't copy 3s down because it's not full. So now we have to follow our instructions. What row is magnesium in? Orbital? Column?
2.
Is S full now?
Yeah.
All right, then when we go over to aluminum, we can copy all of this. What row is aluminum? Or what's its quantum number to be more precise? 3. What orbital?
P.
P.
1.
How do we feel?
Good. Better than other.
Okay, good. Finish out this row. So you've got silicon, phosphorus, sulfur, chlorine, and argon? wanting you to write everything out. I will show you the other way where you don't have to write everything, but the more practice you get writing it, the more likely you are to remember. Hunter. Yes, I'd be happy to. Your handwriting is neat. That's nice. This is the F section. But that one's not full. Yep, because once you take it. It depends on, like the fullness of the orbital depends on what the letter is for it. S is 2. S is full with 2. P is full with 6.
So it would be. Wait, no, yeah, S would be
For sulfur. And then now this P is full because P's maximum is 6. All right, so I'm going to show you now the way to write the condensed electron configuration. That means that you don't have to write all of the previous stuff. Can I move on? Is that okay? Oh, okay, no problem. I'll write it. I know it's hard for me to like shout over all of the fans and the. All right, so now I'm going to show you the condensed. That's what it's called, condensed electron configuration. And condensed just means that you don't have to write all of the stuff that came before. You still have to write some of it, but not all of it. All right, so I am going to pick a random element. I'm going to pick arsenic as my example. It's AS. So here are your instructions for writing condensed electron configuration. And these are firm rules, you can't deviate from them. Find the preceding, I'll explain what that means in a minute, noble gas. Find the preceding noble gas. Write its symbol in square brackets. And then I guess your third step would be to continue your electron configuration from where you left off. I'll explain that in a second. Preceding means the one that comes before it. So you can't just pick any random element or any random noble gas. You have to pick the one that comes immediately before, not after, not the one that's closest, the one that comes before. So arsenic is in the 4th row. So I would have to choose the noble gas that is in the 3rd row. Do you remember what column the noble gases are in? 8A. So the noble gas that's in 8A, that's in the 3rd row, is argon. So I'm going to put that in square brackets. That's what it means by square brackets. Say that again, Carter? Because krypton comes after arsenic, not before. It's not the one that's closest, it's the one that comes before. Okay, so if that's the case, we're at argon now, because what those brackets mean is that everything up to argon. So what I'm saying is that, like, I understand that you know that this means 1s2, 2s2, 2p6, 3s2, 3p6. I just don't have to write it because I'm assuming that you know what this means. Now, because this is just a random friend, we have to find argon on the, arsenic on the periodic table, and now we have to get to this element. That means that we have to go through all of these other elements to get here. So we're in row 4. I'm going to still follow my instructions, and I can't stop at 4s1 because that's not my element. So I'm going to go all the way through the 4s orbital. How do I know that I need to do that? Because arsenic is way over here. And I have to, it's like kind of like a typewriter. You have to make it all the way to this element. So the s orbital now is full. What do? I have to keep going through the periodic table. So I'm going to follow my instructions, write the quantum number. What's the quantum number, though, for this section?
3.
It's 3. How do you know that? You wrote it down on your periodic table. Hopefully. What orbital is this? D. Do we have to go all the way through it? Yes. Yes, we do. Because arsenic is here. And if we didn't go all the way through, we wouldn't make it to arsenic. It would be like getting tackled on the 1-yard line. Sad days.
Wait, but why are we doing that?
So that we don't have to write. We're just saving ourselves from this.
Okay, it'll make sense.
It will. It will.
Where do we get the 3 from?
That's a good question. Remember when you were writing things on your periodic table? I had you write the 3 here.
Oh, I didn't.
That's where that comes from.
Wait, why are we using the ones that are in the why are we using the ones that are
Say that again, Carter.
why do you use column 2?
We're trying to get. We have to go through all of this narrative. Here is where, like, here is the last one is to get. All right, so we are good. The bell is going to ring in 2 minutes. This is what I want you to do. I want you to put this away. I know that your homework, it says it's due probably on Wednesday. Is that true?
Friday.
Oh, good. Okay, perfect. So then what we're going to do is, you guys are already doing a great job of understanding this. I can tell because of your questions. This is confusing, and it's hard to get. So we're going to pick this back up on Wednesday when we have next class. So I don't want you to look at maybe those questions on the first half of page 2. We learned that last time. You can do those. If you want to do something, do that. But I don't want you to look at any of the rest of it until next time, okay? I have some homeworks to hand back.